Okay, so now let's see the Carnot cycle as an example of a reversible cycle, so that you see what I mean. That's the Carnot cycle, the paradigmatic textbook cycle. We're going to go slowly over it, describing each step along the process. I need two things. I'm going to be thinking of the simplest system. So again, it's an expansive system made of a single component or pure substance. And I will be able to represent its equilibrium states, as you know, in a two-dimensional VP diagram. So this is volume here, this is pressure. I'm going to make it large to be able to draw. And physically, if you want to have an intuition of what the system is doing, it is our container that is closed by a piston. Okay, so the piston is sitting maybe here in the beginning in one position, say B1, so that's a volume enclosed inside your gas is somewhere here, filling this uniformly because the system is in thermodynamic equilibrium, meaning that it has a well-defined pressure as well. So its state is characterized by V1. V1 is sitting somewhere here, and this is state 1, if you like. And if you know the equation of state, then you can calculate what the temperature is that corresponds to V and P. It doesn't have to be the ideal gas one, it could be, but it doesn't have to be. And this temperature is what you are going to call T hot, okay? That's that temperature. And what you do is now you bring in contact with your system, you bring a heat source, which is at that precise temperature, okay? And you establish thermal contact with this heat source, which is sitting down here. And what you will do is you will do a quasi-static reversible expansion while in contact with that heat source. So it's an isotherm or an isothermal process. And you're going to bring your volume up to there. Let me mark where the volume was before. So this is position B1 here, and this position here is B2. Okay, so if you want to draw this in the VP representation, what you're doing is following an isotherm, and remember that isotherms were like equilateral hyperbolas, like that. It doesn't look very well. Let me try to do it a bit better. Something like that, okay? And of course it has to pass through one somehow. Okay, so you do that and you end up having a larger volume, V2. So you are sitting in another equilibrium state somewhere there, okay? So in this process, what has happened in terms of energetics, okay? So, well, you are expanding the system. It means you are making work on the environment, which means that the work in this first reversible stroke, which is an isothermal stroke, you are making a negative work, okay? So you can write it like this, which is less than 0. And how about the heat in this case? Well, you are in contact with a heat source, so you can absorb heat. And if you're expanding your system and you are keeping the temperature constant at a high level because you are in thermal equilibrium with the heat source that you are in contact with, then it means that you must absorb heat from the source to keep the temperature of the system from dropping as you expand. And this means that this temperature is going to be larger than 0, okay? So then we go to the second step. And in the second step, we're going to remove this heat bath from here, and we're going to insulate thermally our piston. So I'm going to draw some thermal insulation around it, like that. So a double wall type of thing. So this is a perfect insulator, adiabatic, ideal. And what we're going to do is we are going to continue expanding. So we are going to go a little bit further up here. Again, I mark the position here, and this is B3. So remember that, well, I'm drawing isotherms and adiabats. I'm going to draw now of an ideal gas. I said before, it doesn't have to be an ideal gas for a Carnot cycle. It's just any gas, okay? I'm just drawing the way that the isotherms of the ideal gas look like. They could be slightly different. So we are going to do this second expansion while the system is insulated, again, quasi-statically. And if we do quasi-static process in a thermally insulated container, we know that this is going to be reversible. We learned that in the previous chapter. And we also learned that adiabats, they look kind of like that, at least for the, well, that's not what I wanted, something like this. Okay, so we follow the adiabat and we increase a little bit further the volume up to V3. So what is happening in this process? Well, in this process that goes from 2 to 3, I still make work on the environment, so the work is still negative, but because we are talking about an adiabatic process, of course the heat absorbed is 0. There's no heat absorption because there is an insulator. Okay, so once you are here, then you can check what your pressure is. So you would have an equilibrium state characterized by the volume and the pressure, and you calculate what temperature does your system have, or you can go and measure what temperature your system has, and this is the temperature level that you are going to call the cold temperature. Okay, so what you're going to do now is you're going to remove your thermal insulation out of your container, and you're going to bring into the problem a heat source at that new temperature T cold. You're going to put it here, T cold, and you are going to establish thermal contact with your system. Okay, and now what you will do is to move the piston down somewhere there, let's say. Okay, so you go from B3 to B4. Okay, and as you're doing that, you are doing it quasi-statically, you are in contact with a cold heat source, so you are again moving along an isotherm. Okay, and this stroke is also a reversible stroke, and it will look something better than this for sure, and it will look something like that, let's say. Okay, and you stop at a certain point. Let's say you stop here in state 4. Okay, now what happens to the system in this new stroke? We are going to from 3 to 4. We are making work on the system, so now the work is going to be positive, and we are doing an isothermal process in which we have to keep the temperature of our gas constant, but we are compressing it. So the gas will like to heat up, but we are keeping the temperature constant, and to make that possible, the gas has to release some heat into the heat bath. So it means that the heat is going to be negative in this case. Okay, so we release some heat, we go up to 4, and then the final little bit of the process is to close the cycle. Okay, to close the cycle, I just have to move my piston to where it was before. Okay, so it will go all the way up to so I have to do something else. I have to switch off this heat bath, of course, and I have to insulate again thermally my piston. Right, so I put my insulation back. I do that process that I just described. I compress the system a little further, and now, because I'm insulated and I'm doing a quasi-static adiabatic process, I move along an adiabat, and this adiabat is such that it cuts my system at the same initial state we started. Okay, so we have closed the cycle, and this thermodynamic cycle is made of 2 isotherms and 2 adiabats, and these processes are themselves, each of them, reversible. So the whole cycle is reversible. Okay, and we are making this reversible cycle following the clockwise direction, and we learned that if you do that in a quasi-static process, you are making a net work into the environment, so that the net work is going to be negative. Okay, and in this case, the net work is, well, you have contributions both from the isothermal strokes and from the adiabatic strokes. I forgot to write the last little bit. When you go from 4 to 1, work is still positive, so the environment has to make the work, and the heat is going to be 0 in this case because it's adiabatic. What I can tell you for sure is that the total work, which is the sum of all the works that I'm going to do, is always going to be negative. Okay, so this means I'm running it as an engine, and in the same way I could run the cycle in reverse and it would work as a refrigerator. Okay, so the Carnot cycle, like you can see, it only needs thermal insulation for the adiabatic strokes, and it only needs to operate between 2 heat baths, right? So in that sense, it's the only ideal or reversible engine cycle that can operate between two heat baths. But it's not the only cycle that effectively operates between two temperature levels. So there are other thermodynamic cycles that we are going to study that involve actually infinitely many heat baths, but in the end of the day, only two heat baths matter effectively. And in this sense, these other ideal cycles are like the Carnot cycle, because effectively they operate, or the only two temperatures that matter are some hot temperature and some cold temperature. So you can directly compare certain ideal thermodynamic cycles with the Carnot cycle. And right now we're going to see another ideal cycle, which is the Otto cycle, that is different fundamentally from these two temperature type of cycles. And the Carnot cycle cannot be directly compared with the Otto cycle, as we're going to see in a moment.